Good morning. This is the Math Department, grade 11, session 2 on complex numbers. The objectives of this session are: first, we start with revision on previous session, correction of the homework given in session 1. We will talk about the equality of two complex numbers. We will talk about the powers of I. We will talk about the conjugate of a complex number. We will also talk about the quotient of two complex numbers. Let's start with revision on previous session, correction of the homework given in session 1. Write the following complex numbers in algebraic form, specifying the real part and the imaginary part. First one, z equals 2 plus 3i all squared. Here, if you develop this as you develop the traditional identity a plus b squared, this is a squared plus 2ab plus b squared, keeping in mind that I squared is minus 1, and simplifying, you will get this, and consequently the real part will be negative 5, and the imaginary part will be 12. Proceeding to the next one, z equals 1 minus I all to the 4. First, it's very important to split this 4 and to rewrite it as an exponent of an exponent. So it's 2 to the 2. So you start by developing the inner bracket. It's a squared minus 2ab plus b squared. Simplifying I squared and writing this as minus 1, you will get minus 2i all to the power 2. Expanding this, it will be 4i squared. Finally, it's minus 4. So the real part is negative 4, and the imaginary part is 0. Z equals 2 over 3i into 2 plus I all squared. It's better to start with the identity 2 plus I all squared. It's a squared plus 2ab plus b squared. Before expanding this, it's better to simplify the inner bracket and to write it as a 3 plus 4i. Now you develop or you expand, you will get minus 8 over 3 plus 2i. So the real part is minus 8 over z, and the imaginary part, again, it's the coefficient of I, so it's 2. It's incorrect to say that the imaginary part is 2i. Some students do this, and this is not accepted. Let's talk now about the equality of two complex numbers. When do we say that two complex numbers are equal? Given the two complex numbers, z1 equals a1 plus ib1, and z2 is another complex number, a2 plus ib2. For sure, all these a1, b1, a2, b2 are all real numbers. First, we say that a complex number is equal to the zero complex number. So these two complex numbers are equal, but this is a special case where the other complex number is 0. So a complex number is said to be the zero complex number if and only if its real part and the imaginary part are both zeros. So a1 equals b1 equals 0. In general, if you have two complex numbers, z1 and z2, for these two complex numbers to be equal, then the real part of the first complex number must be equal to the real part of the other one, and the imaginary part of the first complex number must be equal to the other, or to the imaginary part of the second complex number. Consequently, a1 must be equal to a2, and b1 must be equal to b2. Example, determine the real numbers x and y such that 2x minus 8 plus I into 3y minus 4 is equal to 5x plus 2iy plus y plus xy. There are two ways to solve this problem. One of the ways is to keep the left-hand side components to the left, and to keep all the components which are on the right, keep them on the right. So you can see that the left-hand side is a complex number whose real part and whose imaginary part are clear. On the right-hand side, you may group or regroup the real parts alone and the imaginary parts alone. So you will get A complex number to the left is equal to a complex number to the right. And the real parts of each complex number are clear, and the imaginary parts of each complex number are clear. So that's why we can equate the real part to the real part and the imaginary part to the imaginary part. You will get a system of two equations with two unknowns. You can do some algebra to do this system. It's very easy here. You can do it without the use of calculator, but the use of calculator is for sure accepted, and that's why you are allowed to use your calculator. So the two solutions, or the roots of this system for x and y are, the values are x equals -3 and y equals 1. Let's talk now about the powers of I. For sure, I to the 1 is I. I squared, this is the basic component of this chapter. I squared is the imaginary number whose square is -1. But what about I cube? We cannot keep I cube as I cube. We have to reduce it. I cube is I squared times I, and I squared is -1, so the final answer is -I. What about I to the 4? I to the 4 is I squared times I squared, which is -1 times -1, which is 1. What if we continue with I to the 5? I to the 5 is I to the 4 times I, but I to the 4 is just calculated to be 1, so that's 1 times I, so that's I. What about I to the 6? Similarly, you will get -1. What about I to the 7? It's -I. As you can see, we are repeating ourselves here. I is I to the 5 is I squared is -1, and I to the 6 is also -1. I power 3 is -I, and I to the 7 is -I. And finally, I to the 8 is I squared power 4, or I4 power 2, it's 1. What can you notice here? We notice that if I is raised to any exponent which is a multiple of 4, so if the exponent of I is a multiple of 4, like 8, like 12, like 16, like 20, like 400. So if I is raised to any multiple of 4, then the answer must be 1, because this will be I to the 4 to a certain integer, and this will give 1. Examples, what about I20? I20 is I to the 4 to the 5, but I to the 4 is 1, so 1 to the 5 will be 1. What about I to the 61? Here you should think of a number which is the greatest number, which is a multiple of 4 but less than 61. 60. So this I to the 61 must be seen as the product of two powers of I to the 60 times an I. But I to the 60, since 60 is a multiple of 4, it can be written as 4 to the 15, and it will give 1 times I, this will give I. What about I to the power 102? The largest integer, which is a multiple of 4 and which is smaller than 102, is 100. So it's better to split it into multiple of 4, I100, times I squared. I100 is 4 to the 25, which is 1, times I squared, which is -1. I to the 163, again, the largest integer, which is a multiple of 4 and which is less than 163, is 160. So it will be written as 4 to the 40, and that's I to the 160 times I to the 3, but I to the 60, since 60 is, or 4 times 4, 160. I to the 160, I to the 160 is a multiple. 160 is a multiple of 4, and consequently that's 1 times I3. So, but I3 itself is -I, so the answer will be -I. Application 1, match each of the following to its proper answer. Start by thinking about I to the power 2, 4, 5. Before proceeding with this video, you should always think and try to stop the video and to get the answer by yourself. Now, 245 is not a multiple of 4. Yet, you should think of the largest number, which is less than 245, but a multiple of 4. For sure, you can use calculator. Actually, the number 245, the largest multiple of 4, which is less than 245, is 244. You can try this using calculator. So the best is to write it as 244 times an I. I to the power 244 will be 1. You will be left with an I. What about I to the 20? 2020, I mean I to the 2020. I to the 2020. 2020 itself is a multiple of 4. You can try your calculator. That's why this is directly 1. What about I to the power 562? 562 is not a multiple of 4. You should think of the remainder in case you divide. Actually, the largest number, which is a multiple of 4, less than 562 is 560, which means if you divide 562 by 4, the remainder will be 2. So I to the 560 will give 1, and you will be left with I squared, which is minus 1. Finally, I to the 2019, the largest multiple of 4 less than 2019 is 216. So I to the 216 will be 1, and you will be left with I cubed, and I cubed is again minus I. Another application, write an algebraic form of the following complex numbers. Z equals 1 plus I to the power 7. For sure, here you cannot directly expand the power 7 here. You should put a plan like it's 1 plus I squared to the power 3 times 1 plus I. It's better to start with 1 plus I squared. It's a squared plus 2ab plus b squared. Simplifying this, it will be 2i power 3 times 1 plus I. But what about 2i power 3? 2 power 3 will be 8, but I power 3 will be minus I. So this will be minus 8i into 1 plus I. Expanding this, it will be minus 8i minus 8i squared. Do not forget here that I squared is negative 1, so the final answer is 8 minus 8i. Another application, z equals 1 minus I to the power 14. It's much better to start like expanding 1 minus I to the 2. Then 2 to the 7 will be okay. Now, a squared minus 2ab plus b squared. Simplifying this, it will be minus 2i power 7. Now, it will be minus 2 to the 7 times I to the 7. So you will keep the minus since the exponent is odd. So it's minus 128. But I to the 7 is nothing but I to the 4 times I to the 3. And I to the 4 is 1. And I to the 3 is negative I. Finally, this is 128i. Last one, expand this one. Is it better here to write this bracket multiplied by itself and start developing or expanding this one? Or it's better to simplify what is there inside the bracket than trying to expand or to utilize the exponent? For sure, here it's much better to start simplifying the expression which is inside the brackets. So 1 is 1, I is I squared is negative I cubed is negative I to the 4 is 1, I to the 5 is I to the 4 times I, which is I. Simplifying this, it will be, so all the expression inside the brackets, all this expression is reduced to 1 plus I. Now 1 plus I to the power 2 will be a squared plus 2ab plus b squared, which is negative 1 here. So the final answer is 2i. Let us talk now about, we talk about the conjugate of a complex number. What do we mean by the conjugate of a complex number and why we need it? The conjugate of a complex number z equals a plus ib is another complex number, a minus ib, denoted by z bar. So z bar is nothing but the conjugate. It's just a notation that symbolizes the conjugate of z. If z is a plus ib, so you simply go to a minus ib. So you keep the real part as it is, but you consider the opposite of the imaginary part. So, for example, what is the conjugate of the complex number z equals 4 plus 5i? It will be the complex number z bar equals 4 minus 5i. What about the conjugate of the complex number 4 minus 3i? So you have to keep the real part as 4, but the imaginary number must be switched to positive. So now z bar is 4 plus 3i. What is the conjugate of the complex number minus 4? Minus 4 is a complex number which is real, so you have no imaginary part here. So you cannot multiply the imaginary part by 0 since it's 0, by minus since it's 0 in all cases. So this complex number will be equal to its conjugate. Note here that whenever the complex number is real, then it will be equal to its conjugate. What if the complex number is a pure imaginary, like this complex number, half I? So if I say you want to keep the real part, anyway, the real part is 0, or it's not written. But the imaginary part is half, so the conjugate will be minus half I. Note here that the conjugate to this complex number is minus half I, which is also considered as its opposite. So is the opposite considered to be the conjugate of the complex number? This is only in the case when the complex number is pure imaginary. Okay, let us complete this table. I will give you the complex number. You have to think of the complex number which is its conjugate. So if the complex number is half minus 7i, its conjugate is half plus 7i. If the complex number is minus 5i, its conjugate will be 5i. If the complex number is I minus 1 over 2, so the conjugate should be, some students may say it will be I plus 1 over 2. They are mistaken. This is not the way we find the conjugate number. Be careful to the order here. In this left-hand side, we have written the imaginary part to the left and the real part to the right. So be careful whenever you are finding the conjugate. You need to keep the real part, which is minus half here. So you need to keep the minus for the 1, but I, the coefficient of I should be multiplied minus 1. So the conjugate will be minus I minus 1 over 2. So the real part is or stays untouched. Anyway, if you can proceed to this complex number, 2 minus radical 2. Note here that this complex number is a pure real. So the conjugate of this complex number and the complex plane is the same. It's 2 minus radical 2. What about this complex number? This complex number you may expand, you may not, but actually you have to multiply the imaginary part by minus, so it will be plus 3i. Now, what about this complex number? X plus iy plus I. Where is the real part of this complex number? X. So you have to keep it as X. What is the imaginary part of this complex number? If you take I common, you will get y plus 1. So this and that are both the imaginary parts, or the imaginary part. They both constitute the imaginary part, so you multiply it by minus. There is a property here about a complex number and its conjugate. When you multiply a complex number by its conjugate, we need this property in our session or later in this chapter. Whenever you multiply a complex number by its conjugate, it will be like this: a plus ib multiplied by a minus ib. It's like x plus y into x minus y, applying the difference of two squares identity. So it's a squared minus ib squared. But do not forget here that I squared is negative 1. So the answer is a squared plus b squared. You can use this directly from now on. Whenever you are multiplying by a complex number by its conjugate, so a complex number by its conjugate, you will get directly the real part squared plus the imaginary part squared. And note here that the answer is real. There will be no I in the answer. So for all complex numbers, we have z times z bar equals the real part of z squared plus the imaginary part of z squared. Application, calculate this times that. Since these two numbers are conjugate, you don't need to expand and to waste your time. You can directly say it's the real part squared, which is 2 squared, plus the imaginary part. Imaginary part is a 3, not 3i. So imaginary part squared, so you will get 13. If you develop one by one, you will get the same answer for sure. Now, these two complex numbers are conjugates. So the answer is written directly as real part squared plus imaginary part squared, and that's 73 over 36. What about the product of these two complex numbers? Since x is real, so I'm sure that these two complex numbers are conjugate. The real part is x plus 1, and the imaginary part is a 3. So I don't need to develop and waste my time. The answer can be obtained directly as the real part squared plus the imaginary part squared. Again, the product of these two complex numbers, it will be the real part squared, which is x in this case, and the imaginary part, which is clarified here by taking I common. So the final answer will be x squared plus the imaginary part squared, which is 1 plus y all squared. Geometric representation of the conjugate of a complex number. We check this GeoGebra activity. As you know, each complex number is represented by a point in the plane. We explained this in the previous session. For example, consider this point M, whose coordinates are -1, -1. So the point M is here at -1, -1. What about its conjugate? Its conjugate, you will keep the x part, which is -1, but it will be -1 plus I. So z bar will be, in this case, -1 plus I, and consequently, the image of z bar will be here. What can you notice about these two complex numbers, about these two images? There's a clear symmetry around, or these are reflected in the x-axis. Let me change, for example, the value of A or of B. For example, if M is the complex number, if M is the image of the complex number 2i, so the coordinates of M are 0, 2. So since Z is 2i, since B is 2 and A is 0, then Z bar will be -2i, -2i, so it will be here, M prime, the image of Z bar will be 0, -2, and again, you will notice that M and M prime, the images of a complex number and its conjugate, are symmetrical with respect to the x-axis. What if the complex number or the image of the complex number lies on the x-axis? What if z is a 3? If z is a 3 and its image is a 3, 0, then z bar will be also 3. So m prime in this case will be also 0, 3 and 3, 0, and consequently m and m prime are coinciding here because z and z prime are equal because z is pure real. Last example. If m, for example, is 6, -1, if m is 6, -1, since z is 6 minus I, then the conjugate will be 6 plus I, and consequently, these 2 points will be symmetrical around the x-axis. As a conclusion, M, which is the image of Z, and M prime, which is the image of Z bar, are symmetric with respect to the x-axis. So if you consider in the complex plane a point mxy, which is the image of the complex number z, then m1, the image of z bar, which is the conjugate of z, x minus iy, m and m1 will be symmetrical with respect to the x-axis. What about the quotient of two complex numbers? How do we find the quotient of two complex numbers? We've studied already how to add two complex numbers, how to subtract two complex numbers, and how to multiply two complex numbers, and even how to do like an exponent for a complex number, like 1 plus 3i all squared or all cubed. But how can we do like 1 minus I over 2 plus 3i? How can we write this as one complex number in its algebraic form? To find the algebraic form of the quotient of two complex numbers, we multiply by the conjugate of the denominator. That is, for all complex numbers z1 and z2, we have z1 over z2, for sure taking into consideration that z2 is a non-zero complex number. You multiply by the conjugate of the denominator. So you multiply by z2 bar up and down. Why is that, you think? Because when you multiply z2 times z2 bar, you will get rid of I, and consequently you can get the algebraic form of the quotient. Let me see an example here. Write in algebraic form the complex number z equals 2 plus 3i over 4 minus I. How can we write the answer as one complex number in algebraic form where the real part is clear and the imaginary part is clear? So first, you multiply by the conjugate of the denominator. So you multiply up and down by 4 plus I. For the numerator, you need to expand, like 2 times 4 is 8, 2 times I is 2i, 3i times 4 is 12i, 3i times I is negative 3. Denominator, you should write the answer directly, the real part squared plus the imaginary part squared. Consequently, we got rid of I in the denominator. So you can split now and write the complex number clearly in its algebraic form. Another example, z equals 1 minus I over 3 plus 2i multiplying by the conjugate. Following the same process, we expand the numerator. Denominator directly go to the real part squared plus imaginary part squared. This will be 1 minus 5i over 13. Final answer, 1 over 13 as a clearly real part plus I into minus 5 over 13. Another example, z equals I over x minus 3i, where x is real number. Again, you multiply by the conjugate of the denominator, which is x plus 3i. Expanding for the numerator, it will be ix plus 3i squared. Denominator, you go directly to the real part squared plus the imaginary part squared. Simplifying the 3i squared in the numerator, you will get ix minus 3 over x squared plus 9. Again, notice that we have no I in the denominator, and this will allow us to write this complex number in its algebraic form, because you can split the real part to be minus 3 over x squared plus 9 plus I into the imaginary part x plus 9. Consequently, this is the real part and this is the imaginary part. Thank you.